I'd like everyone to notice, Monday and Tuesday of next week, we're going to talk about the greenhouse effect and climate change. I want to do this with great care. I have a giant chip on my shoulder about science in general.
A chip?
I'm I am a moderately educated but lifelong scientist. I've been into the sciences since I was little, and I like to think I'm a fairly logical person. I'm into like puzzles and math and whatnot. And as a teacher, I want to be like welcoming to all of my students, and I try not to judge your decision making or your families or your bad habits, because I've been all over the map in my life, and I'm in no position to throw any rocks in my giant glass house. But I have this like tremendous chip on my shoulder when it comes to public conversations about science. The funny thing about science is it is inherently looking for error. Scientists are always searching for the flaw. Science is never done. Science is this constant progress of improvement. So no scientist would ever tell you that the knowledge is perfect. That is unscientific by its nature. Unlike belief systems that are deemed to be perfect and total, science is the opposite. It is inherently imperfect and never finished. So there's plenty of room in the sciences to debate the details, but the thing that really chaps my hide is when people deny fundamentals of knowledge. It would be like me saying that I do not believe the heart moves blood in your body.
2 plus 2 does not equal 4. I know it.
It would be like saying that I don't believe in gravity.
Oh, it's floating.
When people say, I'm kind of milking it because I look forward to this lecture every year. When people say that they don't believe in climate change, I am just stunned by the audacity of that utter ignorance of science. Because it's not like every scientist agrees about every detail. That's the whole point of science. It's never over. We will always be fighting for better knowledge. That's the whole point of science. It's like the way that it works. But nobody has that like impulse to doubt their dentist. Be like, nah, bro, you're doing it wrong. Here, just give me the chisel. I got this. And I don't think anybody would like walk up to a suspension bridge, go look at like the Golden Gate and be like, you know, I know 1,000 engineers have worked on this, but I don't think we need that big support tower there. We would never second guess an engineer. You don't like get on an airplane and say you don't believe in flight. And you would not get on an airplane and say, I'm sure we don't need that wing. We implicitly, every day, show our respect, appreciation, and commitment to science. We get behind the wheel, and we don't like take off the steering wheel or cut the seatbelt.
You know?
We don't like perform our own like heart surgery because we know that science has this like robust body of knowledge which we rely on daily. And yet somehow people think the climate thing is different. So what I want to do today is finish our introduction to the basic atmosphere stuff, and then I want to show you a few of the things that we do know about climate and how we know them. So very quickly, I got to finish up yesterday because I'm going to need the whiteboard. This is called a convection cell. All the following vocabulary you got to know. So everybody knows this is called a convection cell. One cell, convection cell. You know that convection cell is driven by differences in temperature, which are the same as saying differences in pressure. You might know from yesterday, if I didn't totally blow it, that there are 6 of them on the Earth. It's just a detail of the astronomy we live in, that there are 6 on the Earth. And you may have written down, in case I didn't tell you, write them now, but they're called the polar, temperate, and tropical, aka Farrell and Hadley. All those underlined terms you must know. The Farrell and Hadley is easy to confuse. Okay. Those are the people who describe them, yeah. Those are science nerds.
What was science nerds? Always naming things after yourselves.
I know, the audacity.
So you might be remembered.
Can't you thank your sponsors?
Yeah. No Toyota cells.
Vaseline. You also know, I think, that because the planet is spinning underneath those cells, we get what are called the global trade currents made by the global trade winds. The trades which go from east to west, and the westerlies which go from west to east. You got to know that. In our major oceans, the rotation is set by spinning the planet, and the equator has the most powerful energy. You remember me running around the classroom yesterday?
Not very much, do we get?
Yeah. Good idea.
Yeah, bro.
Do these on the board correspond to this study goal, or are they just
All of that was all number 13. Everything I've said so far is me just explaining how the atmosphere works. I wanted to give you the very basics of observational atmospherics. This is just what we know about the world we live in. Here, Gary.
Vaseline.
Will you nuke that 4 minutes? And if it's not hot enough to almost burn you, microwave it longer? I think 4 minutes should be just enough to burn you.
He wants to burn.
Show me the blister, bro. I know it's distracting. I'm just setting up a demo I'd like to show you at the end of our period. It'll be very tempting to focus only on this. Pay no attention to the beep sounds over there. So, are we all in on number 13? Everybody's got all that vocab, and you can explain all the arrows on that computer screen. You want to ask me a question? Yeah, bro?
So, is high and low pressure determined respectively by cold and hot temperature?
Well, there are two separate matters here. Yes, the driving energy source is input of temperature. Yes. Input of heat, sorry. The part where a lot of my students get kind of confused is, if it's hot, why is there low pressure? And the low pressure results from the transfer of that heat. In other words, by adding heat, things move. And that movement defines the high and the low pressure. Does that answer your question, or just befuddle the terminology? Am I just muddying the waters?
No, I get it.
Okay. All right. So let's do a few other study goals that are going to be important for me to make my argument. Please write somewhere in your notes that we're going to come back to number 14. You'll have to remind me. I'm going to forget. This is a new point for me this year. I'm going to skip number 14 for now. Remember I told you I'm organizing the unit differently? You remind me that I skipped number 14. Number 15, simple vocab. What is the difference between climate and weather? Do not read your book to me.
Climate is overall change. Weather is minute changes in areas.
Yeah, one way to say this is long-term trends versus individual events. For example, you might say that Kobe Bryant's career is roughly going downhill these days. Is that accurate, by the way?
Yeah.
He's aging, I assume?
No, he's more.
He's old. Yeah.
Turns out
he's
he's a
old. He's
god.
like 24 or something? No. He's really 26? 36? 34. Yeah, that's old.
His age finally matches his shoe size. Then he has big feet.
How long does that would be?
Anyway. Climate is a long-term trend, like saying his career's going downhill. Weather would be like, oh, he made like three-pointers in a row. That'd be like weather. That'd be like, little small localized event. Not part of the big picture trend, part of the small picture data flow. 36? 34?
37.
Oh, you weren't looking it up? Then what the hell were you doing with your cell phone?
He's like 30, he was born in 1978. So
What?
He was born in 1978.
78, so he'd be 36, I know. Okay. So climate is long-term trend, weather is little blips. A lot of people say, oh my God, how can there be global warming? Boston was really cold yesterday. Don't confound weather and climate. I cannot tell you how many times I've been at the supermarket and some idiot will say, God, it's so hot today, this global warming is really getting out of control. Okay, at least you believe in global warming, thank you. But no, that's not, they're totally different.
Increasing frequency of heat waves, this global warming.
Next.
Can you bring me the tray out of the freezer?
Next. How do scientists make a statement that humans are causing climate change? If you watch the screaming heads on television, it won't take long to find someone who says, oh, but climate change is natural. Students, is it or is it not natural?
Yes. Yes
It
and no.
is partially.
Who says yes, climate change is natural? Who says no, climate change is not natural? Welch, maybe you can clarify for us. Why'd you raise your hand twice?
There's an overall pattern that the Earth has in its temperature, but humans themselves are increasing the speed at which this pattern happens.
Yeah, I mean, technically we are reversing our natural trend, but also there are both natural climate change and then human stuff. Yeah.
So if the Earth like cools and warms on its own naturally, right now is it naturally cooling or warming on its own?
Naturally cooling.
So we're going the opposite way.
That's right.
Why is it cooling?
We know what the planet should be doing, and it's not.
To do that?
How do we know?
Asking and asking.
Yeah, but you know, how do we know that this isn't just some natural fluke? I mean, if we know in the past things have gone up and down, how do we know it's not just going up on its own? Like, how do we know that it's humans?
The speed.
That used to be something to do with that.
Oh no,
No, this is just
Because it's so rapid.
Then,
because it's so rapid. It sure is rapid.
Was it started after humans started being on the industrial?
That would be a very compelling correlation, which is accurate. But that alone would not be enough convincing evidence for scientists to make such a bold claim as to say that humans are changing climate. What is the difference?
we release gases.
Are
We know
are we releasing
happen.
gases that wouldn't normally be in the atmosphere to contribute to global warming?
We are releasing gases that we know trap heat very well. But you know, the atmosphere is complicated. By the way, I can play devil's advocate to all your logic. You can try to say something smart and I'll dumb it down, no matter what you say, to the point of sounding like I belong on nighttime television. I can out-dumb the dumbest news anchor. Or news commentator, whatever you call them.
Whoa, die.
By the way, I don't want to distract from this other conversation that we're having because I think it's more interesting, but I'd like to point out that I've used blue dye and red dye as a mere indicator of which water will be cold because it's sitting in ice cubes and which water will be hot because it's sitting in 4 minutes of microwave water. You know what I mean? Well, we'll come back to the demo. Don't worry. I'll remind you what's going on as we get there. But I'd like everybody to look at number 17, please. Yeah.
Question. What makes the temperature increase as the lake turns to ice and sun?
We have had a more sudden and more extreme temperature change than any other century we know of. The last century had the most rapid heating in the history of temperature that we know of. You were asking, right? Hook, I mean?
No.
About high pressure, low pressure, which one is made by, is it made by temperature, is it made by temperature?
Does it apply the same in water?
What do you think?
No. I mean, yeah.
Okay. Now here's the funny part. If this is hot, shouldn't that be high pressure? How is this cold water flowing to high pressure?
Because it's not this is low.
Right, because the high pressure has risen because of the heat, right? Once you add the energy, the fluids will respond, and that creates the low and the high. Yes?
Why is it like when like a news anchor or someone or like a weatherman says, "Oh, we have a high pressure zone going over us, so it's really hot." Why? Why do they say that?
I think that they mean it the other way around.
Okay.
But anyway. I'll come back to that.
Low pressure zone.
I'll come back to that.
So it'll be rain.
I'll come back to that. But there was this guy named Milutin Milankovitch, what number? 16. Yeah, right. Thank you. Milutin Milankovitch, number 16. He was a Serbian mathematician. If you know anything about Serbs, they're usually like really hardworking, and some people describe them as being pessimistic or bitter.
And they start World War.
Politically, the Serbs have been sort of kicked around. I don't want to talk too much politics, but as a mathematician, Milutin Milankovitch was perfectly Serbian. He set out to disprove what we call astronomical perfection. He said, those circles can't be round. Milutin Milankovitch wanted to prove that there are flaws in the geometry of our galaxy. He wanted to say, look, they can't be perfectly round. The gravity adds up, too many confounding factors. By the way, does everybody see what's happening?
Yeah.
Move then. Look what's happening. As soon as I move my cart, it really stirs the water.
The red is going to the top of the blue.
The red is on top of the blue because you've heated water, which has risen, smashed into itself, and created high pressure. And at the same time, because they're connected, you've cooled this water, which is falling, creating low pressure, and piling up here. So you have a high pressure where all that cold water is thumping against the bottom, and all this high pressure where the hot water is thumping against the top, and those high pressures are spreading to the low pressures at the opposite sides. Everybody like that? The temperature differential created a pressure differential. That pressure differential is moving the fluid. Pretty soon it'll all be purple. Are we done with the demo? I'll leave it, but anything else I need to say about the memo? The demo? What memo? I didn't get the memo. Yeah.
So, in the middle,
Uh-huh.
is the red hot still, or is it like...
Oh yes, if you had a laser thermometer, this water is significantly hotter than... Oh, I can feel it. Significantly different. Yeah.
So, on the convection cell, when you say that cold air is falling,
Uh-huh.
so does that mean in the high pressure zone, does that mean it's hot?
You see, this is that thing. You can get high pressure of cold stuff and high pressure of high stuff. The pressure is dictated by the amount of collisions between the molecules.
So since the Earth is hot and the cold air is heating, it's
Heating up over time. Yeah. So, easy to confuse these things. Because it's hot, it rises. Because it rises, it creates high pressure. That's one. Because it's cold, it falls. Because it's falling, it creates high pressure. Agreed? What drives them left to right is the fact that all this air has left, so now there's low, and all of this is piled up, so now it's high. And as it goes, that drives the transfer of energy to build the heat that will make it rise. Up and down is a response to temperature. The left and right is a response to the pressure that's created by the temperature.
So can you say that the pressure is all you can place together, where it's not all piled up?
That's a fact. Getting purple. Everybody good? Check it out. Here's what Milutin Milankovitch described. He got a lot of sharp pencils, set his alarm clock, used fancy telescopes, and he measured 3 irregularities in our solar system. They are, number 1, the shape of our orbit changes. Look at me. You grab a hula hoop, and you squeeze it, or pull it, or squeeze it. You know how to do that with a hula hoop? Our Earth's orbit does exactly that. So there will be some years when the shape of the orbit makes for a hotter planet, and some years where the shape of the orbit is colder, and some years where it's just average. Yeah.
Yeah, in Pluto's cycle for 20 years, it's because of the shape of the orbit, it's closer to the sun than Neptune.
Irregularities in the galaxy make sense because each of those planetary bodies adds and subtracts from the gravity of the others. If they were in synchronous orbit around the sun, they would be in synchronous shape. Right? Because they would all be like the same sun gravity as they moved around in the track.
Or that somewhere there was an argument that was classifying Pluto as not a planet because of it.
Oh, because it's in orbit? I don't like that argument, but I hear you. Next. That shape changes every 100,000 years. And what you get from that, we now know, is that some years there's like a trend of heating on Earth, some years a trend of cooling, and that sine wave has a period of 100,000. So average shape to hottest shape to average, and coldest shape back to average is 100,000 years. Hotter, average, colder, average, that's 100,000 years. Yeah?
Wait till what are we in right now?
Colder, right?
I don't know about any of the individual cycles. Milankovitch cycle number 2, the angle of the dangle is changing. In other words, everybody knows that I say it's 23.5 degrees. Well, it's 23.5 degrees for this millennium. But if my model gets old in about 2,000 or 3,000 years, I'll have to adjust that by about 1/10 of a degree. The bottom line is that angle slightly varies. Yeah?
Why are certain years like it always colder or warmer? Is it all the same like average distance from the sun? Is that
Because there's a different amount of heat gain in the northern and southern hemispheres because the southern hemisphere holds a lot more water. Right? So global average temperature is driven by one hemisphere's seasons more than the other hemisphere's seasons.
So is it not colder or warmer on other planets that don't have oceans?
There may be other factors involved, but you hit the point of this issue. Yeah. That last one, every 40,000 years. And this one, it's called axial wobble. You've got to know these. 26,000 years. So please look up. The Milankovitch cycles are shape of the orbit, variation of the tilt, and axial wobble, 100,000, 40,000, and 26,000 years.
What is
Axial wobble, I can give you a visual, different reasons, but I'll give you a visual. You take a quarter, spin it on the table, agreed? And you've all seen what happens. That quarter will have a very tight axis, right? But as it slows down, what happens to that axis? You know that thing that it does right before it flattens out? Okay.
The Earth is about to flatten out.
The Earth is not about to flatten out. It is a completely different set of factors. However, the Earth does have, as a visual only, an axial wobble. James Mel, if you're using the phone behind that camera case on your desk, I swear I will snap every long bone in your body and take the short ones and grind them up between two bricks. I will make a bloody pulp of you, James Mel. Then I will smear you in the street and drive over it with my car, James Mel. Then I'll sprinkle sugar on it so the seagulls eat it. Milankovitch discovered all three of these cycles, and then he wrote a book called The Astronomical Theory of Climate Change. He wrote it in the 1940s, way before calculators and computers and all that stuff.
Wow.
He was just like a really diligent mathematician who like carried all the decimal places and used like infinite significant figures, and pretty much like he was a mathematician's mathematician. This guy was like the most hardworking, burly dude. Yeah.
Yeah, can I see Austin, please? It's for yearbook.
Let's see, Austin Coombs. Is this how you would like to spend your period? Because if so, that's fine with me.
No.
Next. I mean, Austin, if you're down for the yearbook, bro, go do that. I love the yearbook. I hate the concept of interrupting school. Like, Dave Mel.
He wasn't alive for like all these cycles.
Oh God, no. He just saw the shit. Because of science and math. You see, like, if you get a few data points, you can tell it's not a straight line, but it's a curvy line, right? And if you get enough data points, you can find the sine wave that matches it. And you got enough data points and enough sine wave points and enough like math and science to nail it. Like nowadays, that we can use hundreds of years of satellite data, like light refraction, and I don't know what the F we do. Turns out, he was right within many decimal places of percentage accuracy. Considering he did this in the 1940s, with relatively clumsy telescopes, like kind of low budget. You know, Serbia was not like a global superpower in the 1940s. But you know, the dude put like 30 years of his life into this. And this was like his pursuit. Like he literally had like whiteboards and whiteboards of math. And he nailed it. Nailed it. Oh, everybody was like, wow, that's pretty cool. He found imperfections in the galaxy, but who cares?
30 years?
Nowadays, just so that you know, we have found other natural rhythms which affect global temperatures. The point is, we can take stages of glaciation in hot weather and cold weather going back many hundreds of thousands of years, and when all those little sine waves add up, you're going to get a really hot year. And when all of those troughs add up, you're going to get a really cold year. And when they cancel out, you get average years. Right? You guys all know how wave cancellation and wave summation works? Is that something that you've done in your school life?
It has been done.
Milankovitch got the party started with what we call the fundamental astronomical theory of climate change. And since Milankovitch, now that we have like satellites and better telescopes and like all kinds of other cool science, we know, for example, that there is a rhythm to solar flare cycles. In other words, the sun's activity has a heartbeat. And we know how that affects climate. We know how the rhythm of solar flares affects climate. We know further how changes in the dust content of the galaxy affect climate. So in years that you have a lot of comets which block sunlight, you get a little less radiation hitting the Earth, and that's a very small rise in global temperatures, or a very small drop in global temperatures, because we've shaded the Earth a little bit with space dust. Apparently, when the magnetic polarity of the Earth changes, there is a brief momentary change in the amount of solar radiation which heats the planet, and we can factor that in. And I am not very smart, but if you talk to science nerds, we can look at the known history of temperatures, and we know what's natural. And you know what's interesting? There are a few blips like that one that don't make sense. And then we look in the geologic record and we can find the volcano or the meteor or whatever. I am stunned that people believe a scientist would call it man-made climate change and go, stupid, there's natural climate change, you silly scientists. And like really, literally, like believe that the scientific community hasn't thought of that. I mean, imagine how you would feel like you go to the doctor and you say, hey, doctor, I've got this giant tumor in my neck. And the doctor goes, stupid, there's fat all over the human body. Like, will you pay your doctor? Like, would you get a second opinion? Like, isn't there some process of discerning what is normal from the abnormal? Of course there is. Do you remember how adding heat and adding cold changes? Check this out. I believe this is number 17, the ocean conveyor belt current.
Okay, so how's that going to change?
We know that there are parts of our planet where you get a lot of wind. So if you get a lot of wind, you get a lot of evaporation. You get a lot of evaporation, you get a lot of cooling, and you get a lot of cooling, things sink. Remember when you get a lot of cooling, water sinks? Yeah? Remember how when you get a lot of heating, water spreads? So we know a few things about our planet that, you know, this big glob of ocean here, and this big glob of ocean there, and that little glob of ocean right there, you know, they're exposed to different amounts of sunlight, different amounts of wind, and so they're going to have different average temperatures. And when you add up all the hot waters and the cold waters, you get one of those. You've got warm water across the top and cold water across the bottom. Before everything turned purple, you saw that, right? If I had kept the cold cold and I had kept the hot hot, you would still notice that. Unfortunately, the dye is bleeding, but this is still hot. This is significantly colder. With my bare hands, I can feel the difference. Was there a hand?
Yes. So it's kind of basically like a big convection zone?
That's right, because there's different amounts of energy being put into different parts of the system. One's hotter, one's colder. Yeah?
Wait, why is there like a definite top and bottom? It doesn't, it's kind of arbitrary.
Because there's a distinct temperature difference.
Because there's more water on the bottom. Like, there's so much more land on the top and more ocean on the bottom, so it's like colder down there.
No, I don't think that we're looking at the same detail. Ask your question again.
I was going to say, so it's like the warm flows to the top and the cold down below, but what makes it considered the top or the bottom?
Oh, because the ocean is deep.
So it is.
So like you can measure the flow of water in the top roughly 200 feet, and the water cruising across the bottom of the ocean, and they're in distinct opposite directions.
Oh, no, I meant like the north and south. Because on there it looks like the warm is all. Yeah.
Because the round map has been stretched at the poles to make it a rectangular image? Is that your question?
I think he's saying like since it's like shallow and deep, like he looks like a cyclone, but aren't they on top of each other? Like
They are on top of each other. The lighter color is surface water, the darker color is deep water. I got a better picture for you. Maybe this will help. Does that address your question?
Yeah, I got it. No, it's not.
For real?
I didn't realize.
Because I want to help you, I still don't know what the hell you're talking about. That helps?
I got it. I didn't realize that.
It's like, why does the warmer water go north of Australia, whereas the colder water goes south of Australia?
Well, I don't know. Maybe there's differences in the depth, or maybe, I don't know. That's a very good question. Yeah.
And the other
Maybe
question-
across that channel, I don't know, yeah.
And then why is the cold, deep water salty versus the warm water is less salty?
So remember what I said creates the cooling in the North Atlantic? Basically, it's all driven by the North Atlantic. Give me a second to explain. It takes a little work. Keep in mind that the primary temperature differential, if you're going to really try to understand which one drives the most, like the single biggest input of energy here, like the most rapidly moving water, is here. Please look up the North Atlantic, because it's very, very windy. And for a big chunk of the North Atlantic, there's very, very little cloud cover. So you all know what happens when you blow across the top of hot soup, right? It cools off and you blow away a bunch of steam, right? The water that reaches that spot is extremely hot, and the wind evaporates it away. So when you evaporate salt water, what's left? Salt, right? And does everybody realize that water plus salt will be heavier than water without salt? Saltier water will sink. So because it's colder and because it's saltier, it really sinks. I've got a number for you that might blow you away. If you were to measure the water flux at the North Atlantic Ocean, there are 5 billion gallons of water sinking per second. It's spread out, so it's not like a giant sinkhole with dolphins getting sucked down. But the net change in temperature causes sinking of 5 billion gallons per second. It's a lot of energy. Okay? Now here's the fun part. Because you're taking away the heat, that sinks. And because you're adding heat, this gets hotter and hotter. So it comes over really hot. This is hotter than it should be. And then it goes away. And when it rises again, it rises really cold. Everybody see that? Those two areas of upwelling in the Indian Ocean and the North Pacific Ocean, where the cold water comes to the surface? That makes sense? So check this out. India has a natural air conditioner. So does Alaska. Right? Because there's cold water coming to the surface. It's like a cooling trend. Does that make sense to everybody? It's a heat sink. Air conditioner. Good? And it takes away the heat somewhere else. Look at it like Europe has a natural heater. See that? How the North Atlantic has a delivery of hot water from somewhere else. Like Indian Ocean water is being brought to Europe. Now this is very significant. I want everybody to notice something. If you look at this latitude, England is basically the same latitude as Mongolia and whatever the F that is. Quebec. In other words, you've got tundra right here, and if you go that exact same latitude to this side, you've got grass and roses. If you go a little further, Russia, which is right over there, has grasslands and wheat production, where Canada has tundra. Anybody know why that is? Because they've got a heater providing them warm water vapor with lots of rain. Everybody understand that?
Yeah.
Are we all on the same page right now? I only got 7 minutes. This is one of those big aha moments. Let me finish. Everybody understand what I'm saying about delivering the hot water makes a heater for the North Atlantic? Okay. I want to take a step back now. Step back. We can measure the energy transfer of ocean circulation currents. So when we talk about climate, we know how much of the heat will stay over here and how much of the heat will go over there. Europe is artificially 2 degrees hotter because of this conveyor belt. Indonesia is about 0.7 degrees cooler because of the conveyor belt. The North Pacific is about 1.1 degrees cooler because of the conveyor belt. I want to remind everybody that it's not like scientists are making up what's natural about our planet's climate. Scientists can measure these things, map them. We have thousands and thousands of careers built on intellectual rigor to assemble this body of knowledge, just like your medical system does, just like your civil engineering does, just like your aeronautic engineering industry is built on the work of thousands of people's careers doing very careful work with really sharp pencils and a lot of headaches and a lot of coffee. Nobody agree with me on this so far? And here's one really scary thing about the ocean conveyor belt. Right up there, we've got a lot of wind and a lot of sunlight, so a lot of salt water is evaporating, and it's sinking because it's really, really salty. Do we agree? What would happen to really salty water if you added a bunch of fresh water?
It becomes less salty.
Less salty, right? Do we agree with that?
No.
Do you all know that like fresh water floats on top of salt water? Everybody know that fact? Fresh floats on top of salt?
Fact.
So here comes a fun one. If the planet gets hotter, does anybody see a source of a lot of fresh water in that neighborhood? Yeah, maybe that big old chunk of ice called Greenland. You guys know it was called Greenland, so everybody would buy real estate in the wrong spot. Yep. And they would avoid Iceland, which was the very nice place to live. You knew that? Real estate scam? Was that your aha moment? You didn't know that? Icy Greenland. Real estate scam. Yeah, no maps. They didn't have like satellite photography. Now back to me, friggin' Swedes. They will cheat you. They look nice, but they are devilish. Okay, now watch me. As the planet heats up, we already know Greenland's been melting. You can map that. There's very clear data about Greenland's melting in the last 25, 30 years.
Poor Greenland.
And so this part of the ocean is getting less and less salty. So even though it's still evaporating heat, it's stopped moving. The ocean conveyor belt is collapsing. So here's what we know.
Europe's getting colder.
We know that Europe is getting colder and it's getting drier. Those are two facts that have been long established. In a period of global warming, Europe will have extreme chilling. That's a fun fact, isn't it?
Very fun.
And furthermore, Europe and Russia will have a drought because there's less water evaporating because the ocean's so cold. Because we're not bringing over the heater anymore. The ocean conveyor has stopped. So we've taken away the heat source. In other words, where's that heat staying now? The Indian Ocean is getting hotter, steamier. Bangladesh just had the wettest monsoon season last year that they've ever had. Disastrous flooding, coastal areas all underwater. Because it rained more than ever, because there's more evaporation than ever in the Indian Ocean. And the Pacific Ocean is also getting hotter. Local fishermen will tell you this. Because the heat is no longer being transferred away on the conveyor belt. We've stopped moving those waters. Because we've added so much fresh water to the North Atlantic that we've basically turned off the most powerful current in the ocean. How's that for an amazing little observation? And it ties together very simple data that anybody knows. You can ask any Russian farmer, how have the rains been in the last 25 years? And they'll be like, well, you know, the last 10 have been the driest we ever had. And you ask somebody who lives in London, how have your temperatures been? You know, overall, we had those hot spells, but dang, it's been really cooling off. Because the heater stopped bringing hot water vapor. Question?
I was confused why the water from like in the Europe area isn't the same as one in India. It's like if Europe isn't getting their heat, it's just getting transferred to India.
The heat is not leaving India. Keep in mind that when you're moving this water, you see how the water, you see that arrow is going across the Indian Ocean and delivering that heat this way? You've basically slowed that transfer. Yeah?
So why is it sinking in the North Atlantic if it's so hot or is it cold over?
In the North Atlantic, it sinks naturally because of the change in density. All that evaporation.
Does it have to do with the warm water coming over it?
So it's warm to begin with, and you hit it with a bunch of wind, it will evaporate, cool and dense, and drop. It gets saltier and colder. So two things that make it denser. But we've challenged one of those. We've added fresh water. So now we've reversed that density trend, so it's stopped pumping. Yeah.
So is hot water moving, or why is the cold current going up? Is it because
It's being drawn up by that. Remember this?
Oh.
Like we're drawing water up. So look, I made cold water come this way to replace the hot water going that way. Right?
It's basically it's a change of pressure, right? So there's a bunch of cold water at the bottom, so you want to try to go up.
What's that?
Like it's pressure, right? So like a lot of cold water at the bottom wants to come up.
Yeah, I mean it's basically just slamming into there, so it's like diffusing around the circle. There's like the powerful parts of the chain and then the draw parts of the chain. The push and the pull, I guess. How can I help further with this?
So what happens when ice or Greenland loses all its glaciers?
Well, I think you'll see that in your lifetime, so I guess you'll find out soon. It seems pretty clear that you'll see that. I mean, not all. Obviously, I don't think we're going to lose every one. But I think you're going to see a lot of that in your lifetime. Yeah?
The book said that Europe was 5 to 10 degrees hotter because of the current. Yeah, so.
I don't want to dispute your book. I thought it was 4. Maybe we're talking about air temperature versus land temperature versus water temperature, which you know are obviously going to be different.
Celsius versus Fahrenheit.
Heat capacity. And it might be measuring in Celsius. Celsius equals 9 degrees, one or the other. There's another thing I did not get to do today. I wanted to explain what we know about the past. Oh, we have until 10:04. I can do that. Please go to number 18.
I can't even see any of the hands right now.
It's okay.
We're good.
Are you going to call me out? We're good. Here are some other things that we know. We know what temperatures have been. And seriously, one of the most sad complaints about climate change. They just invented thermometers like 300 years ago. How do you know the temperature before thermometers?
Nice.
You know, because there's a lot of ways to figure out what temperature was. Well, science. Here's what we know. First of all, we've got about 400 years of temperature records that we've had thermometers. A few hundred years, it's easy. Galileo invented them in the early 1600s. They were pretty well calibrated and being used by many scientists by the 1700s. We've got like pretty extreme accuracy and global distributions of temperature and long-term records. Starting in the late 1700s, by the 1800s, you've got temperature records all over the planet. So we've got a couple hundred years of thermometers. But, you know, how do we get further than that? I'm talking about temperatures of hundreds of thousands of years ago. How do I know such a thing? Number one, ice cores. Check this out. You go to a place that has a lot of snow. A place like, you know, Antarctica. Someday if you're bored, check out my Andrill posters. And then you drill a hole through the snow. And when you drill a hole through the snow, look inside that pipe, you get these things called ice cores. It's like the core of the drill bit is a big lump of ice. And if you look very closely, that lady's such a fox. If you look very closely, all of that fallen snow has trapped little tiny layers, because you guys know that when snow falls, it's sort of fluffy, right? And then when it freezes, there's like little air pockets in it. And when you pile up more snow on top, you keep accumulating little layers of the atmosphere. And you can date those layers of the atmosphere because there's dust and pollen in each layer. So in places where you have a continuous accumulation of snow, like the cold places, then each of those layers of snow has discrete layers of organic sediment that you can carbon date to figure out the date and age of that layer, and then you can slice the core into little tiny slivers of snow, and then check this out, you put it in a vacuum, suck out the air, let it melt, and you measure the ratio of gases in the atmosphere from 8,000 years ago, and different gases have different activity levels depending on temperature. You know that every gas has a different boiling temperature, right? So likewise, gases will disappear from the atmosphere or become more common depending on temperature. And then you get the ratio of all of those gases. And write down these numbers. Using ice cores, I can give you 650,000 years of temperature records with 0.4 degree accuracy for each decade. We can stretch that to 1 million in the next couple of years. We're just going through data now.